In this video we're going to be looking at vectors in component form, but a few further examples that also involve velocity vectors. So a typical question we get in tests or exams are looking at boats or aeroplanes that are affected by wind. We've got to look at how we can get the correct velocity vector so we essentially end up where we want to end up. So let's take a look at this question here. So we've got two airports. And we're given their distance by this displacement vector here. And then we know that they want to go from A to B, and then we start talking about speed and we start talking about velocity vectors. So the first thing we want to do is put our displacement vector on a diagram. We don't want to mix displacement and velocity together. So 600i plus 200j just gives us a rough idea in the direction and essentially what it looks like. So 600i plus 200j. Now we are in kilometers, which means we are strictly looking at displacement. So that will be on a diagram by itself. Okay, so we know we want to go in that direction. The next bit of information tells us an aircraft can maintain a steady speed and we have a wind blowing. As soon as we talk about that, we are looking at velocity vectors, so we're actually going to draw a different diagram for that. Okay, so we know for my velocity vector, so this one is looking at velocity. Okay, so we have a wind of 30i take 20j, which is, let's say, around here, this direction. So we've got 30i take 20j. All of that is kilometers per hour. And we also know that the aircraft can maintain a steady speed. So we don't actually put that on our diagram because that can't be put in our diagram on just yet. But we know it's got a speed of 390 kilometers per hour. So let's just leave that to the side. So that's the speed of the plane. Okay, so we would like to know what the velocity vector is that the pilot should set so that the wind speed plus that velocity vector causes the plane to travel essentially to where it wants to go. So what we would say to ourselves, right, what are we actually doing? We are trying to see the wind's velocity plus the plane's velocity, putting those two together. We want to end up, so our resultant, we want to end up on the path of the airport. So that's essentially where we want to end up. So putting that all onto a diagram, let's see what that looks like. Let's get a different color here. Okay, so the only thing I know about my resultant vector is that it is in this direction here. So my resultant velocity vector, so essentially this right here. So I've got this information and I've got some clues about this. The only thing I know about my resultant velocity vector is its direction, because it is in the same direction, because it has to go along the direction for to travel from A to B. So if something is in the same direction, it has to be a scalar multiple of the original vector. So the original displacement vector was 600i plus 200j. Now that was its displacement, but I'm not interested in displacement, I'm interested in velocity. So if something is in the exact same direction, then I know it has to be some scalar multiple of that original vector, because that's the only clue I've got. The clue I've got is it is in that direction. So it is lambda, or I can put mu here if I would like. It is some multiple of this original vector here because it's in the same direction. Now that's my resultant, that's where I'd like to end up, which means the plane's velocity that the pilot needs to set will need to be meeting that direction, essentially, somewhere along that line. I just need to know it hits that line somewhere. So this purple thing here is AI plus BJ, which according to the question is essentially the velocity vector of the plane. So let's use all of that information and put it into some mathematical equations. So let's look at the wind's vector. velocity vector. So the wind's velocity vector we know from the question is 30I take 20J plus the plane's velocity vector, which I actually don't know, that's the question what I'm going to find. And my resultant vector is some scalar multiple of my displacement vector, because I need to end up in that direction. So a common question that gets asked is, well, how can you just chuck this and make this a kilometers per hour? Can you literally just do that? No, what we're doing here is the question tells us this is velocity, so it has to be speed, which is kilometers per hour. The question wants us to find this, and we know that the wind speed plus the plane speed will give us the resulting speed. So the wind plus the plane gives us this essentially here. Now we don't know what that velocity vector is, but the only information that we know is that it goes in this direction here. And what we know about direction with vectors is that if something is in the same direction, it has to be a scalar multiple of the original. That is how I can get this equation here. So using that, let's go back to this information. Now I just need to do some algebraic solving, and then I can solve to get my vector. So if I equate my I components from this side, I've got 30 plus A is equal to 600 lambda, and that's equating my I components. I then equate my J components, which gives me B take 20 is equal to 200 lambda. Now this makes it difficult because I've actually got three unknowns. We've got A, B, and lambda. But the question isn't actually interested in lambda. We don't want to find that resultant velocity vector. Not yet anyway. So what I have done is I've actually done a bit of simultaneous equations, and I've just done a bit of solving. So for this question here, I'll just get a different color. I've then got lambda by itself. So I've dealt with this one. And lambda is then equal to A plus 30 over 600. So using that, I've then substituted lambda into that equation there, which gives me B take 20 equals to 200. Instead of lambda, I put this value in here that I've just arranged. A plus 30 on 600. So that can cancel with that. That's 1, that's a 3, which becomes B take 20 equals A on 3 plus 30 on 3. And we know that this just gives me 10, which means that B is going to be A on 3 plus 10 plus 20. Therefore, B can be expressed as A on 3 plus 30. Okay, so I've got a few equations there. Now let's go back to the question and see what other information we're given. We know from this information that we discussed here that we've got the plane speed as 390 kilometers per hour. And if we look at the plane, it has this velocity vector. And the magnitude of a velocity vector gives us its speed. So if we use that information, we can actually get some other, equations for A and B. So the magnitude of AI plus BJ, which is the plane's velocity vector, is equal to 390 because the speed is 390 kilometers per hour. So that means that A squared plus B squared, and the square root of that gives me 390. So solving from that, that means that if I square both sides, A squared plus B squared equals to 390 squared. Now what I've actually done here is I've gone back and I've substituted in. So I know that from this bit here, B is A on 3 plus 30, and I've just substituted that into here. So rewriting that, it is A squared plus, instead of B, I've written what we had before, A on 3 plus 30, all squared equals 390 squared. Now, this makes it much easier because we're only dealing with one variable, which is A. So putting that into solve or solving it algebraically, you actually get two values. So A gives me two different values here. So if we go back to, because we'll go, okay, well, which value do we use? Can we use both? If we go back to this here, if I substitute those values into A there, I need to make sure that this value of lambda is not negative, because if that value of lambda is negative, then that means that this particular vector here will become a negative, which means its direction is going to change, and we don't want its direction to change. We know we're going this way and we don't want to change anything else about it. So we need to take the value that makes sure that lambda stays positive to keep this direction true. So we want this to stay exactly the same. So if we go back to that, the two values of lambda I'm given, we don't want lambda to be negative because we don't want the direction to change. We want the direction to stay exactly the same. So from that, and we solve, the value of A that we take from our calculator or from our mathematical solving is 360. We then go back to the B value from up here, this one in the rectangle, and we substitute our now A value of 360 into there. So that means that B is going to equal to 150. So given that, the velocity vector that the pilot should set was originally written in this form, and now that we have our values, we can say the velocity vector is 360I plus 150J kilometers per hour. So that's our answer. Now, if we go back to the question, let's actually have a look at what we have found to make sure we actually understand what's happened here. So if we look at this equation that we had up here, this started everything off, this one here. The winds vector plus the planes vector helped us to get some sort of clues to get our resultant velocity vector. So let's use that now. So this that we've got here is the plane. That's the plane's velocity vector. So let's look at what we've done and if that makes sense to us and essentially what all of this information means. So if we look at that equation that I literally just looked at, so the wind's velocity vector plus the plane equals to the resultant vector. The wind's velocity vector was, I think, 30I take 20J. If I add that to the plane's velocity vector, which I have just worked out to be 360I plus 150J, if I add those together, I end up getting 390I plus 130J, which is my resultant velocity vector. So this vector here is essentially the vector for here. Now, if we've done this correctly, which we have, and we've used quite a bit of information, then this velocity vector here should be a scalar multiple, because it's in the same direction, it should be a scalar multiple of our original displacement vector, which was 600I plus 200J. And we can actually check that. So if I compare the two, so this is my displacement vector that I've got, and this is my resultant velocity vector. If I compare the two, then they should have a common ratio between my I and my J components. So if I divide them and work them out, so let's choose a different color. So 600 divided by 390 should be in the same ratio, that should share the same ratio as this, which it does. So if I divide both of them, yes, they are a scalar multiple of the other, which then brings me even further if a question asks, okay, so I know that lambda was some scalar multiple of 600I plus, what was it, 200J. You could then go one step further and figure out lambda. So if you go back to any one of these equations here, for example, you could go back to this one. You know what A is now, so if you substitute A into there, so if you've got 30 plus A, sorry, let's get a different color here. So using that equation that I circled just then, 30 plus A equals 600 lambda from my resultant velocity vector, or from this here, I know what A is now, 360. If I substitute 360 into here, 30 plus 360 equals 600 lambda. And I get 390 is that. So into my calculator, if I put 390 divided by 600, I will get my value of lambda, which is essentially going to be 0.65, which makes sense because my velocity vector that I put on my resultant was this. Putting that value into there, 0.65 times that. If I've done this correctly and I've worked all of this out correctly, and I multiply all of these out, and that should essentially equal my resultant vector, which was 390 I plus 132j. So this is just showing you why it's important to use the direction of the initial displacement vector to figure out what you're trying to find out.